Good morning, ladies and gentlemen. Welcome to another episode of our web seminar Wednesday series, CEO Online, CEO Prepared for Future. Today we have Erik Berg here from Broetje Automation. This is special efforts today because Mr. Berg is in Chicago right now. So it's 2 a.m. in Chicago, and he still agreed to deliver his lecture to you today. So I think that this receives special recognition, so we're glad to have him here. Before we start with this presentation, as usual, let me give you the details of our format. Please keep your microphone and your camera switched off during the first part of the event. Mr. Berg will roughly need 30 to 35 minutes for his presentation, and then after that we still have plenty of time for discussion, for your questions. Feel free to post your questions in the chat during the presentation already, and I will read them in the second in the later Q&A session, or simply raise your hand in the second part, the Q&A session, and we will unmute you, and then you can ask your question right away. Mr. Berg will talk today about smart automation for higher flexibility and sustainability of composite production. I think that's a very exciting topic because we want to automate, and at the same time we need to be flexible and react to changes in production. I look very much forward to your presentation, Mr. Berg. Enjoy.
Thank you for the introduction, Mr. Brenken. Yeah, my name is Erik Berg. I'm working at Broetje Automation since 2015, and I would like to introduce you into this webinar about the smart automation for higher flexibility and sustainability of composite production. And at first, I would like to introduce a bit Broetje Automation. It's commonly, I hope, known, but still, I would like to introduce you very briefly. Our mission is equipping the factory of the future. We are a company that is not only the equipment itself, but also introducing all the services, requirements, planning, and digitization and process development, which is required for factories that are being set up and changed. The factory itself is our core competence, where we equip with our automated machinery and all the equipment that we deliver. And of the future stands for the up-to-date technology we are delivering, but not only up-to-date technology, also our know-how goes into the newest products and processes that we are constantly in development. Our customers are the global aerospace industry. The big knowns, I guess, are the Boeing and Airbus company, besides all the medium and smaller aircraft manufacturers that are standing right in front of you. Broetje Automation is basically part of most civil aircraft. So if you have been flying the last time, probably you have been flying in a machine that is on one part being assembled or produced on Broetje machinery. We already have 40 years of experience. Beginning of 1979, with our external activities in tool making, after relocation to Wiefelstede, we did found during the years several subsidiaries like BA USA. We acquired companies like Hydro Control in Jadderberg, found special service units, developed market unique machinery, and also relocated the US workshop to Chicago, where I currently am. And I think the most relevant one is the acquiring of the MAG Composites Germany, which is merged into BA Composites, so Broetje Automation Composites in 2013, and recently have been included into the main company, Broetje Automation itself, so which is now head of all composite development in Broetje. We are in 3 continents, 7 countries, with not only service departments, but also engineering departments. For sure, our main one in Rastede. Probably some maybe would like to come over. It's quite nice and new shop floor we have there, and it's from 2016. Then we have our US shop floor, which I'm currently, then the France subsidiary, UK Chester, which is near the Broughton side. In China, in Shanghai, we have a site, and also in Japan, Nagoya. Our product portfolio is not only the automated equipment around composite fastening and assembly, we also operate in the smart processes area for high sophisticated process technology and all the toolings that you need for operation. And also with our subsidiary Compose to Complete, we do assembly line integrations and the digitalization of all the services and solutions we have. This is the key enabling services for equipping the factory of the future. We are mostly known for the fastening machines, so a very brief introduction into some pictures of it. So for instance, our only development, PowerWays, which is an aerospace robot designed for the requirements in aerospace, like high stiffness and positional accuracy, and for sure all the different assembly cells for riveting and drilling, which are required in aerospace. But also we're doing all stuff around digitalization in processes, for instance, every topic around augmented reality, which can be brought into manufacturing, is also part of our development. Besides also AGVs, which we developed in the last years very with high effort to bring sanding systems with cobots up to market available technology. And this is our brief overview about the composite systems. We have the industry known composite systems like the fiber replacement systems, which are redesigned and newly designed during the last years and have been further developed within the last years. And also we have our own market unique composite preforming systems, which is something which is very market unique and is going to be one key part, I guess, for the next generation aircraft manufacturing. And also we are also developing all processes that are around the automated equipment to handle and to move machine components or part components from station to station, like sorting and kitting. This is only one part of it, and all equipment required for complete manufacturing system can be delivered by us. I will go brief into some trends we see in the recent years in the aerospace industry, coming from CFRP parts. Oh, sorry, this is still in German, but CFRP parts are commonly done for bigger structures in pre-preg material. The Pioneers A350 and 787 basically set those standards, which are currently also up to date. So we have a pre-preg based wing, a pre-preg based fuselage, which are more long-haul aircraft with higher passenger capacity, but rather smaller production rates. More recent aircraft programs like the A220 or the MS-21 are small aircraft with still metallic fuselages, but CFRP wings. The wing are based more on dry fiber and infusion processes rather than on pre-preg, and they are seen for higher production rates and short to medium haul aircraft. So we already see a slight shift, and the next generation aircraft, what we see is the successors of A310, 320 and 737 might be going to CFRP wings, and the manufacturing process tend toward dry fiber and thermoplastics. The classical thermoset pre-preg processes will not be longer dominant, and we also hear everything wants to go out of autoclave. So for the next generation aircraft, just a short wrap up, the skin manufacturing we see the possibility for dry fiber and thermoplastic AFP systems, which are required to be developed for the future manufacturing processes, some already in place and some to be improved. Alternatively, we also develop pick and place technology as a subsidiary of AFP technology, because it might have some benefits on 1 or 2 points there, especially for high rate production. And stiffening profiles, we see going more and more to preforming of structures and then co-curing, so infusion and curing together of the stiffeners with the skin. These can be also seen in recent changes which are done by suppliers or aircraft manufacturers. Here on the left side, you see a spoiler for a wing, which is has been made out of prepreg during up to, I think, 2018. It's with a honeycomb inner structure, hand laminated in a low-cost country, and there's a change to improve this to, for instance, an RTM-based spoiler which has stiffening profiles inside rather than in honeycomb, which is automatically produced and made in Europe. So this is already some changes which are done recently. I'll go into stiffening profiles as I have divided my presentation a bit. The production profile production are going to be, we see, based on dry fiber. So because of the manufacturing philosophy of infusion and curing of skin and stiffeners in one step. So we are going into one-shot infusion technologies. And the reason for this is that dry fiber material can be provided
Jetzt pass auf, da ist gerade ein Webinar.
Can be provided at lower cost. This reduces the storage pricing. The dry fiber components are easier to store and move also, so you have less effort in moving dry fiber parts. The positioning of the profiles are easier to correct after you have placed them with prepreg. You place them and it's very hard to reposition them on a larger scale. You don't have subsequent riveting of components necessary, which saves weight, which is also a very interesting topic for future aircrafts. And outcome is that we need new and efficient manufacturing processes for this, because currently it's more or less hand layup and hand lamination of profiles. But with the profiles, there are some challenges we have. For instance, frames and stringers are very high complexity profiles. There are hardly any identical parts in aircrafts in terms of ribs and stringers, and they have individuality in each of the stringers and frame. For instance, you see here on the right side joggles which are going across thickness increases in the surface of the wing skin or the fuselage skin. Also, you see on the bottom here a frame which is not at all harmonized in radius or web width. So it changes all around the profile during the cross section. And with this, we developed our own continuous preforming systems, and the system basically is already started to being developed in 2007. So we have 15 years already of development in this technology. It is a long way for development of these high effort machines, but it started to getting paid off for the new manufacturing systems, for the new manufacturing of newer aircraft. And this is there's a reason, because we have all the process chains for preforming in one machine. This saves a lot of shop floor space and also saves a lot of handling of parts, which also saves the quality of the part. We have it fully automated, so no manual interference required to change the geometry of the profile or to do adaptations in cutting or something, and the machine is high adaptable to the profile requirements. So with one machine currently, we can produce a high variety of profiles. The production chain in the production system is based on modules which are being set up subsequently to induce the form. We always start with the material storage and setting up stacking with also complex reinforcement plies that we can bring into. Then for dry fiber, we do a fixation also with thermoplastic binder. Then, for instance, if you go to a T-shape profile, we do, for instance, here cutting. So we separate two lines, do a lateral shaping into two Ls with heat and pressure. And after final trimming, we cut off the part so we can store it. This is an example installation we have recently set up. This is a system for stringers up to 18 meters. This is part of a new wing aircraft manufacturing program and has high potential to go into the next generation wing production. And this is something we are very proud of, because this machine can produce all the stringers required for a lower skin for future aircraft system. So one stringer serves, I think, 21 or 22 stringer configurations in length from 18 meters to 1.7 meters, I guess. So this is very highly sophisticated machine. We can lay up 42 material layers, all independently. So each of the material layer can be shaped, can be cut to certain length, and can be formed required to the profile which is being produced. Here also some examples for profile complexity, the jogger that we have, for instance, and also the diving blade. So this height of the T is less than this height here. These are changes which are in the profile and need to be induced in this system. Now I go briefly into the automation of skins and panels. Current challenges we have in skin production is for larger skin fields, we have already a higher degree of automation and technology which is driven by pre-preg. And the most known technologies are tape laying machines and fiber placement machines. These are also characterized by a high usage of supporting materials, so backing films, bagging films, releasing foils, and stuff. And we see that there is a shift to dry fiber, not so much thermoplastic with large skin fields, but more for sure dry fiber with newer programs. On the other hand, the smaller skin fields have a higher complex geometry, and automation was always a bit more difficult. So we had a lot of hand layup with cutting tables and a small degree of fiber placement technology supporting this. So the technology is also driven by pre-preg, also a high usage of supporting material again, but also here we see a shift to dry fiber or also more thermoplastics with new aircraft programs. And we see with the shift from pre-preg to dry fiber or thermoplastics, there are process adaptations for new processes required in the future. This is why we improve our STAXX-AFP systems in the recent years. We have basically 4 sub machines that we have in our portfolio. This is on one hand the STAXX-1700. This is a fully enclosed 16-toe AFP machine, 1/4 or 1/2 inch toe width with a layup area of 1.2 by 1.5 meter. The size of this part is, or the size of the machine itself is container size, standard container size, so it can be easily been trucked and shipped to any facility, being set up within a day and directly ready to produce parts for aircraft or other products. This has been improved since the last years to also, this can only let, I forgot to say, but this is only for 2D applications, so you only can lay up flat. The 3D AFP machine here can also lay up slightly contoured parts, which improves improves the capabilities of the machine by having some degree of 3D layup. And the more interesting ones which have been developed into within the last years, the STAXX-AFP used for thermoset material, but also now very recent we are setting up one for thermoplastics, which we had which we are currently setting up and having in our shop floor. This is a full 3D layup robotic AFP and effector with 16 toes, quarter or half inch. We have the material spools all on one head, so we have the capabilities of automated AFP head change, still also with thermoplastics pre-preg of thermoplastic fire placement. What is, I guess, a market unique feature with thermoplastic layup on a fire placement head. And the design goal was especially to have a lean design which is easy maintainable for the operator of the machine. The net weight of the head is around 280 kilograms with the material 440, so that it can be also manipulated by a standard KUKA robot instead of having high duty robots which are less competitive in different terms of production. And also we have developed a STAXX-1, which is a single toe AFP system, which can lay up anywhere between 1/4 inch to 2 inch. It can lay out thermoset and thermoplastic material and dry fiber, which we are currently also commissioning one system here in Rastede, and the system will also be shown on the JAG fair starting in May in Paris. This can be equipped with all kinds of required equipment like layup tables or cooling. It all depends on the machine. Previously, the machine was more set up for R&D purposes, but we see this machine shifts more and more to manufacturing of real aircraft or aircraft parts, or even different parts like pipes or something. So just a brief introduction to the AFP head itself. We have a very compact design for high performance with 1.4 meter end effector diameter, which is very narrow for a head with spools on board. So we can have a layup radius of 800 to 1000 millimeters in female. Yeah, as I mentioned, suitable for 500 kilogram industrial robot like we have here, because with 8 kilogram material spools 16 times, we have 35% of the total weight are carbon fiber. So this is a recent machine that we are in commissioning, a thermoplastic AFP head on the STAXX-AFP, which is having a laser diode heating source of with 980 nanometers of wavelength, with a power of 6.4 kilowatt. And the laser on head, as you see here on the top right picture, we don't have the laser. Usually the AFP machines with thermoplastics are using optics on the head and having the laser itself in the cabinet and guiding the laser light with a cable, with a glass fiber cable to the system itself. This has some pros, but also the con that you don't have the ability to quickly exchange, and also this cable, the fiber cable, is very prone for damages because of the minimum bending, maximum bending radius or minimum bending radius. The process control here is all done via the CAD system and the layout program itself. We have some abilities to control also temperature and speed profile in the machine, but basically the CAM system all controls what we are doing with this machine. And we have, because in the machine itself, we have selective control for each toe for heating, so we can also lay single toes between some toes without damaging the left and right material on the part. You see here in the center a nice picture of a current being laid up AFP layup out of a PAEK. And the layup rates from thermoplastic we can achieve for PA6, it's around 1 meter per second. For PAEK, we currently have a velocity of 0.3 meter per second, which are currently being improved, but this is our state of the art, what we currently have. Then also one very interesting development from my point of view, if we go also into thinking of sustainability, is with the STAXX-1, there's a single toe fiber placement system, the layup of recycled carbon fibers. This is done especially in a common project with Fraunhofer, Lamilux, Covastor, and others in the project called Scrap Zero. We do lay up here recycled carbon fibers which are aligned within the toe. The chopped fibers are aligned within the toe, and we have two different materials, one thermoplastic matrix material and dry fiber material. The material is been laying up with two wide toes, and the recycled carbon fiber, everyone I think can imagine, familiar being with toes, it has a very low tolerance to toe tension. So you can really easily by hand rip the toes apart into two pieces. And this is a high requirement for the AFP machines because they always work with toe tension to keep the positioning of starts and ends and stuff of the layup. The STAXX-1 is used, as I said, with 2-inch wide material spools. We are laying up 4 plies for testing all directions, and we'll use the Heroes flash lamp as a heating source because we see this as a very good and very high sophisticated heating source for especially dry fiber, but also for low temperature thermoplastic materials. And this system will be shown on the JAC Fair in Paris, starting in, I think, 4th or 5th of May. And everyone is welcome to visit us there. What we currently also do is integration of quality assurance systems into fiber placement machines, where we have camera systems which are monitoring during the layup, not only a picture, but also the complete surface topology of the part. So if a toe is missing, if a gap is growing too big, if the edges of the toe or the layup is misaligned, we see this already within the quality assurance systems because this is something which improves the availability of the machine on the manufacturing, because usually the monitoring is done by operators, and the operator needs to figure out after each ply to see where are the defects, and this system already shows the defects and points the operator to the positions of the defects to being checked and, if required, reworked. So regarding composite integration, we also develop alternatives to AFP systems, and we see some potential upsides on this. We have developed composite handling systems in the recent years where you utilize pneumatic muscles as actuators with own material protective suction cups, which achieve and test a very high positioning accuracy. I will show you some pictures about this, but I think the most interesting part is layup rates. Having layup rates higher than 100 kilogram per hour is a very interesting topic for high rate production of wings or fuselage skins. And we can directly create the lamellates in the infusion mold, just to reduce the requirements of maneuvering the part around and handling of the part, especially if it's dry fiber, what we usually have here, or what they've definitely designed the machine to be using, which dry fiber is very, very prone to damages with handling or with machine handling. And the areas of applications are for sure flatter parts like skins, panels, and floors. On the side, we also can do curvatures, but not as crazy as you can do with fire placement, I guess. So you can see a cell which we have set up with a customer together for a wing skin production with a layup rate above 100 kilogram per hour, with a cutting table on the left side, automatically feeding the positions of the plies being cut to the system, and the system automatically positions them onto the wing skin. And we can achieve very high layup accuracies, like you see here. We have also very sharp laying edges, which is basically not impossible, but very hard to achieve with hand layup. And because you don't have any fraying on the edges here, and the accuracy is very, very high. You can see here a butt joint after robotic layup. It goes from a butt joint here and then an overlap here. A very good, very highly sophisticated system we have developed in the recent years here. So come to a short conclusion of this presentation. We see there are shifting requirements or additional requirements, not only by design for integral designs and higher production rates, but also environmental requirements which are coming into the future aircraft programs, like saving weight, reducing scrap, and saving energy. So we see that there are more smart automations required to balance those requirements that we have. And this leads to new manufacturing methods we would like to introduce, and also which are required to increase the productivity per square meters, for instance, to reduce the shop floor area, and so to reduce the energy being consumed for heating and blocking land grabbing, and also reduces interfaces between machines, which includes or improves the quality of the part themselves. Also, we see a shift to manufacturing methods for integral structures. That means that we do assemble the components before infusion, like we do with the CCPS technology, composite preforming system, which is producing the stiffness and then can being laid up directly on dry fiber skins that probably being used or maybe being used by fire placement, dry fire placement, or pick and place technology. And the replacement of prepreg reduces scrap and supporting materials by a huge extent. And also, we need to increase the machine productivity for production methods for large series to increase the productivity of the machine itself and the availability, like we do with the QS system, where the machine is more prone to do what he wants or should do, like laying up instead of waiting for the operator to check defects. And this is also a necessary necessity for the future to have consistent quality, so you have less scrap, less waste, and less parts which need to be reworked after production. So we see that all the integration of processes require the process depth on the supplier side to increase, and we need, as a manufacturer of machinery, more and more process know-how to be able to improve the automation, to go into a smart automation, and not only substituting existing processes by a machine, but having an overview about all the processes that are being done within the manufacturing system and the manufacturing line. Thank you for your attention. That's it from my side regarding the presentation itself. I'm looking forward to your questions, and on any case, you can contact me also directly. My contacts are shown here, and I would also like to see some of you maybe on the fair in Paris, the JEC, and I'm looking forward to some of your questions, or all of your questions, I guess. So don't hesitate to ask. Thank you.
Yes, thank you very much, Mr. Berg, for this very interesting presentation.